Hi everyone! In this video we're going to be learning about various counting techniques. We're still talking about probability, and so there's a lot of things going on here. The first thing is to solve counting problems using the multiplication rule. So our first example, the fixed price dinner at a restaurant provides the following choices. You get an appetizer, 2 choices, super salad. Entree has 1, 2, 3, 4 choices. And then dessert has 2 choices. How many different meals can be ordered? So ordering such a meal requires 3 separate decisions. You have to choose an appetizer out of the 2 choices, choose an entree out of the 4, and then choose a dessert out of the 2 choices. Okay, so we have our tree diagram here. The first decision is the appetizer, super salad. Then from there, we can pick any of the 4 entrees. And then from each of the 4 entrees, we have to decide which dessert. And this gives us all of our options over here to the right. And so for each choice, we have, like we said, of appetizer, we have 4 choices of entree. And for each of these 4 entree choices, we have 2 choices for dessert. So it's the 2 times the 4, appetizer times choices of entree, and then 2 choices for dessert, for a total of 16 different meals that can be ordered. So notice how we get this result of 16 different meals. We just use multiplication. 2 choices times 4 choices times 2 choices. So our multiplication rule for counting is the following. If a task consists of a sequence of choices in which there are P selections for the first choice, for us that was 2 appetizers, Q selections for the second choice, for us that was 4 choices for entree, R selections for the third choice, that was 2 desserts, and so on, then the task of making these selections can be done by just multiplying the selections, P times Q times R times so on if there was more selections. And so that many different ways of choosing. And so here's another example. The International Air Transport Association assigns 3-letter codes to represent airport locations. So for example, the Fort Lauderdale International Airport is FLL. How many different airport codes are possible? Okay, so notice our multiplication rule. We have 3-letter codes, and the English alphabet has 26 letters. So we have 26 choices for the first letter times 26 choices for the second letter and 26 choices for the third letter, or you can say that's 26 to the 3rd power. So there's 17,576 different airport codes that are possible. All right, here's another one. 3 members from a 14-member committee are to be randomly selected to serve as chair, vice chair, and secretary. The first person selected is the chair, the second is vice chair, and the third is secretary. How many different committee structures are possible? So there's 14 people in the committee, and 3 have to be randomly selected. So notice how this one's going to work. Out of the 14 members, any of them can be the chair, but once you've selected them to be the chair, then they are removed from the remaining choices. So that's why the choice for vice chair is now 13. And once vice chair is selected, they're removed from the remaining choices. So there's 12 people left to choose for secretary. And so there's 2,184 different committee structures that are possible out of these 14 members. So if n is positive or 0, so greater than or equal to 0, and it's an integer, that just means it's like a whole number, 1, 2, 3, so on. The factorial symbol, when you read this n factorial, is defined as the following. So n factorial means the number n times the number less than that, n minus 1, and then you would keep going one number less all the way until you get to 1. So let's say n was 5. This would be 5 times 4 times 3 times 2 times 1. So that's what this notation means when you see factorial. That's how you compute it. So it's an actual operation that you're going to do on a number. And then by definition, just so you're aware, whenever you have 0 factorial, by definition, it actually equals 1. And so also 1 factorial is 1. So the only kind of strange one here is 0 factorial. Just know that it's 1. So now you have just been hired as a book representative for Pearson Education. On your first day, you must travel to 7 schools to introduce yourself. How many different routes are possible? So we're going to just call the 7 schools A through A through G. And then school A can be visited first, second, third, fourth, or all the way up to 7th. So there are 7 choices for school A, like when you will visit it on your route. There are 6 choices for school B, 5 choices for school C, and so on. Because once you visited a school, then you're not going to revisit it. So if you've visited, you can visit school A at any of your 7 stops, but once you visited it or decided when you will, then it's removed from the list of what takes up a spot. Like let's say we visit A first, then there's only 6 other spots on our route that we can choose from to visit school B, and then 5 for school C, and so on. And so the possible routes are 7 choices for A, 6 choices for B, and so on, but we multiply. And so by definition, why we just learned about factorial is because it's a condensed way of writing this idea of 7 times 6 times 5 all the way times 1. So 7 factorial different routes, which is 5,040 different routes that are possible. The next objective, we're going to solve counting problems using what are called permutations. So a permutation is an ordered arrangement in which R objects are chosen from n distinct different objects, where R is either less than n or equal to n. Okay? So real quick before we keep saying things about this, you're choosing R objects, so from a choice of n. So that's why R has to be either equal to the whole number n or less than that. And then repetition is not allowed. So one of the things with permutation is to remember that you're not repeating. And so this symbol, and then this is n permutation R, represents the number of permutations of R objects selected from n objects. Okay, so when you see this, it's letting you know you're doing a permutation. N is the total number of objects, and you're choosing R of them. All right, so here's how this works. So we have the number of permutations of n distinct objects taken R at a time. So you're choosing R out of the n. It's like saying I'm choosing 3 from the 5 total, just for example. And so the number of arrangements of R objects chosen from n objects in which the following is true. Number 1, the n objects are distinct. Number 2, repetition of objects is not allowed. And then number 3, order is important and is given by the formula. So this is our math notation. We have n objects, we're choosing R of them, and we're permuting them. And so the calculation, this is actually your formula. You take n factorial, whatever that number is, you divide it by n minus R factorial. Okay, so let's just evaluate this. So notice the symbol here, it's letting you know you're doing your permutation. So you have your formula, and you're choosing 5 objects out of 7 for part A. For part B, you're choosing 5 out of 5 for permutation. Okay, so here we do part A by hand. Our total number of objects was 7, so the numerator is 7 factorial. On the bottom, we always say how many we're choosing, and we subtract that from the total. So 7 minus 5 factorial. So the simplified one is 7 factorial divided by 2 factorial. And then with factorials, one of the nice things you can do as you're working on simplifying them is as soon as the denominator can divide out, you don't have to keep expanding. So for example here, we were almost done expanding 7 times 6 times 5 all the way down. The last number would have been 1, but because we have 2 factorial in the denominator, we can just stop. We don't have to say 2 times 1, we can just say 2 factorial and divide it with the 2 factorial on bottom, which gives us 2,520. And so take a look at 5 permutation 5, the total was 5. 5 minus 5 is 0. And be careful, remember, 0 factorial is not 0, it's 1. So this is saying 5 factorial over 1. And so 5 factorial is just 5 times 4 times 3 times 2 times 1, which is 120. So this is how you can compute permutations. Okay, so here's an example of using a calculator to do this. And so let me take you over to the calculator and show you how to do it by, we're going to find the buttons. And then here's another one for how to do this in Excel. So what you would do in Excel is you just click on a cell, and then you can type in equal, which tells Excel that it's going to be a formula, and then just say permute, and then 5, choose 5. Okay, so that's just how you would do it in Excel. Let me go ahead and show you on the calculator. Okay, so on the graphing calculator, you want to click Math, and then over to Prob for probability. And then what we want is number 2. And so we're going to go down to 2, enter. Sometimes you have to put the number in first, then hit the button we just did, and then the last number. But in this case, we get to just put in the numbers after we've selected this permutation function. So we wanted 5 permutation 5, which was 120. So that's how you can do it on the TI-84. Okay, so let's take a look at this example. In how many ways can horses in a 10-horse race finish first, second, and third? So let's see if we can use our permutation for this. So 10 horses are distinct. That's good. That's required for permutation. Once a horse crosses the finish line, it won't cross the finish line again. And so in a race, order does matter. So we're going to be able to use our permutation function. And we have 10 horses, and we're choosing 3 of them. So plugging into our formula, this is going to be 10 factorial over 7 factorial. And then notice when you can stop expanding on the numerator at 7 factorial, because what you could do is you could say 10 times 9 times 8 times 7 times 6 times 5 all the way to 1. But it's a little unnecessary to write all that because 7 factorial on the top divides with 7 factorial on the bottom. So just stop expanding once you see that the factorials will divide out. And so we just have 10 times 9 times 8. So there's 720 ways for this to happen. Next, let's solve counting problems using combinations. So a combination is a collection without regard to order. So that's actually the main difference from permutation. Permutation, the order mattered. Combination, the order does not matter. And this is in which R objects are chosen from n distinct objects, where R is less than or equal to n without repetition. So all that's the same for permutation. The new part is that we don't have to worry about order. And so our symbol, this is n choose R, represents the combination, a number of combinations of n distinct objects taken R at a time. So some people say n choose R, you can say n combination R just to make it very clear that we are doing a combination instead of a permutation. So in this example, Roger, Ken, Tom, and Jay are going to play golf. They will randomly select teams of 2 players each. List all possible team combinations. Okay, so all possible combinations with the 4 people of 2 players each. So what is 4, choose 2? And so the list of teams, our options are the following: Roger with Ken, and you can kind of do this one name at a time. So let's say we focus on Roger, we can pair him with Ken, Tom, and Jay. So those are all the combinations for him. Then if we move on, Ken was already paired with Roger, so we can pair Ken with Tom, Ken with Jay, and so the only remaining combination is Tom and Jay. And so the answer is 6, and we did it by hand by just looking at our options of people. And so there's 6 ways of forming 2 from the group of 4 players. Now here's our actual formula. So the number of combinations of n distinct objects chosen or taken R at a time. And so the number of different arrangements of R objects chosen from n objects, where the following is true. Number 1, the n objects are distinct. Number 2, repetition of objects is still not allowed. And then number 3, order is not important this time. And so notice our new formula. This is different from our permutation formula because of this factor of r factorial. So that was new. So we have n factorial on top. We still have n minus r factorial on bottom, but now we have times an r factorial on bottom. All right, so let's calculate the following. 4 choose 1, 6 choose 4, and 6 choose 2. So using our formula for the first one, the numerator is 4, so 4 factorial. And then where there's an n on bottom, we're going to put 4, and we're going to choose 1 from that. So 4 minus 1 factorial. And then our extra r right here, this was 1 in this case, so 1 factorial. So the denominator simplifies to 1 factorial times 3 factorial. But remember, we talked about it, 1 factorial is just 1. And so you can start simplifying. Notice all we had to do here was say 4 times 3 factorial, because this 3 factorial divides out with the 1 on bottom. If that's confusing to you, feel free to expand it all the way. It's just going to take a little more writing. So you could say 4 times 3 times 2 times 1 on top. On bottom, you could say 3 times 2 times 1, and then divide out the common factors. Final answer there was 4. Okay, 6 choose 4. Filling in our formula, we have 6 factorial on top, on bottom, 4 factorial times 2 factorial. And then as we start expanding, in this case, we're going to stop with the bigger factorial from the bottom. So when we start expanding 6 factorial, we say 6 times 5, and then times 4 factorial. Stop there, stop expanding, because we can divide that out with the 4 factorial from the bottom. And then do expand the 2 factorial, it's 2 times 1. So final answer, 15. Last one here, 6 choose 2, 6 factorial on top, 2 factorial times 4 factorial on bottom. And then this time, again, we're going to choose to stop expanding on top once we get the bigger factorial from the bottom, just to save us writing. And so we had the 4 factorials that are going to divide out, and then we just expanded this 2 factorial again. It's very similar to the previous one, it's just the order changed, but we ended up having the same number, so 15. So from the calculator, the same idea that we did with permutation, you just hit the math button, go to probability, and then you'll choose your combination function. And then in Excel, really similar to permutation as well, in any cell, just type in equal sign, and then COMBIN, it's just shortened for combination, and then your first number N, and then comma your second number R. And then you'll get the answer in the cell. Okay, so how many different simple random samples of size 4 can be obtained from a population whose size is 20? All right, so we're going to use our formula where N is 20 and R is 4. And so notice, in this case, the order doesn't matter. That's why we're using combination and not permutation. We can choose any 4 out of the 20 in any order. Okay, so we just fill in our formula where 20 is our N, 4 is our R value, and then we start simplifying. Notice on top, we expand 20 factorial, 20 times 19, all the way until 16 factorial. We can stop expanding there because the 16 factorial on top will divide with the 16 factorial on bottom. And then we did expand the 4 factorial, 4 times 3 times 2 times 1. And what you can do, so you can multiply this out on bottom and on top, but if you also want to, you can divide out any common factor. So let me just show you. If you are going to do this thing by hand, you could say something like 4 divides with 20, and we get 5. And then maybe you could say like 2 divides with 18, and we get 9. And then you can even do 3 divides with 9, and you get 3. If you wanted to simplify it more by hand, you could type that into the calculator, but that's another way to keep it simplifying as you go. Okay, so that answer was 4,845. Okay. Next objective, we're going to solve counting problems involving permutation with non-distinct items. Okay, so let's take a look at this example now. A DNA sequence consists of a series of letters representing a DNA strand that spells out the genetic code. There's 4 possible letters, A, C, G, and T, each representing a specific nucleotide base in the DNA strand. How many distinguishable sequences can be formed using 2 A's, 2 C's, 3 G's, and 1 T? Okay, so each sequence formed will have 8 letters. To construct each sequence, we need to fill in 8 positions with the 8 letters. So one way to do this is to put our 8 positions and then start to look at our options for filling it in. So the process of forming a sequence consists of 4 tasks. So task number 1, choose the positions for the 2 A's. Task 2, choose the positions for the 2 C's. Task 3, the positions for 3 G's. And then task 4, the 1 T. Okay, so notice what we have here. Our first combination is going to be out of the 8 spots, the 8 positions, we're choosing 2 of them to be A's. So that's why it's 8 choose 2. And then we have 6 spots remaining, 6 positions, and we're choosing 2 of them to be C's. Now after all that, we only have 4 spots remaining, 4 positions, and so out of the 4 positions remaining, we have to choose 3 G's. And then last, there's only 1 spot left and 1 T to choose from. And so we multiply all these values. So we multiply the combinations. And so if we use our formula, notice what we have. Our numerators were our position choices, and then our denominators were what we chose, the number 2 in this case for the first one, and then our position number, which was like n, minus what we chose. So that's where 6 came from. It was 8 choose 2, or 8 minus 2. And then just let's do the last one here. We had 1 for n, and then 1 minus 1 for n minus r, and then r was 1. And so a lot of stuff divides out. So instead of typing all this into the calculator, which you could do, you could divide things out beforehand. The 6 factorials on top and bottom, the 4 factorials, the 1 factorials, and so on. And so this becomes 1,680. And we could even expand this factorial on top and divide out a little bit more with the 2's, but this gets us our answer. So there's 1,680 possible distinguishable sequences that can be formed. So permutations with non-distinct items. The number of permutations of n objects, of which n minus 1 are of one kind, n sub 1 are of one kind, n sub 2 are of the second kind, and so on, and then n sub k are of the kth kind, is given by this formula. N factorial on top, the first kind, how many there are of that kind, is n sub 1. So n sub 1 factorial. How many there are of the second kind, that's n sub 2 factorial, and so on, and you multiply all the way to the last kind. For us, there was 2 A's, so there was, the kind was A, and there was 2 of them. Then there was, I think, 3 G's, and so the kind was G, and there was 3 of them, and so on. And then n is just the total number of objects. So for us, it was positions, so it was 8. And if you think about it, we could have said that that was from a total of 2 A's, 2 C's, 3 G's, and 1 T. All right, for this example, how many different vertical arrangements are there of 10 flags if 5 are white, 3 are blue, and 2 are red? So notice we don't have 10 distinct objects because there's multiple flags of the same color. So we seek the number of permutations of n equals 10 objects, where the first kind, which is white, there's 5 of them. The second kind, there's 3 of them, which is blue. And then the third kind, there's 2 of them, which is red. Okay, so using our formula, on top, our n objects, we have 10 factorial. On bottom, we multiply the factorial of each kind. So 5 white, so 5 factorial times 3 factorial of blue times 2 factorial of red. And then notice we start expanding. 5 factorial, we could stop there because we could divide that with the denominator. And then if we simplify, we end up getting 2,520 different vertical arrangements for these flags. All right, so here's a summary of what we've learned. We learned about combinations, permutations with distinct items. And you could do this with replacement. Let me talk about that in just a moment. Permutations of distinct items without replacement, and then permutations of non-distinct items without replacement. So anytime you have replacement, this was the one where we had 3 letter choices for the airport, and you can pick any letters. So we had, if you remember, 26 times 26 times 26. So it just ends up being a power of n. And so that one's kind of the simplest one. But with combination and permutation, remember the main difference is that with permutation, order matters, and then with combination, the order does not matter. All right, our last objective is to compute probabilities involving permutations and combinations. So in the Illinois lottery, an urn contains balls numbered 1 through 52. From this urn, 6 balls are randomly chosen without replacement. For a dollar bet, a player chooses 2 sets of 6 numbers. To win, all 6 numbers must match those chosen from the urn. The order in which the balls are picked does not matter. What is the probability of winning the lottery? Okay, so the size of the sample space is going to be the following. So notice this notation we've seen before. Then this is just saying the number of the sample size. And so we have 52 balls to choose from, and we're choosing 6 of them. So using our combination formula, without repetition, but order doesn't matter, we have 52 factorial on top, 6 factorial times 52 minus 6 factorial on bottom. And then we start simplifying, and we get 20,358,520. So each ticket has 2 chances of winning. If the E is the event where you have a winning ticket, then the number of outcomes of event E is 2. And so the probability of E, which is the probability of a winning ticket, is 2 out of the possible outcomes for the choosing of the balls from the urn. So 2 out of the 20 million something, which is about 0.00000098. And if you make that a percent, it would be 0.000098%. So to make that make a little bit more sense, that's about 1 out of 10 million chance of winning the Illinois lottery. Okay, our last example. A shipment of 120 fasteners that contains 4 defective fasteners was sent to a manufacturing plant. The plant's quality control manager randomly selects and inspects 5 fasteners. What is the probability that exactly 1 of the inspected fasteners is defective? Okay, so the number of ways of choosing 1 defective from the 4 that we're told were defective is just 4 choose 1. And then the number of ways of choosing 4 non-defective fasteners from the remaining 116, because if you just subtract out of the 120 of them, 4 were defective. That means 116 were not defective. So the number of ways of choosing 4 non-defective out of the 116 is just 116 choose 4. So the number of ways of choosing 1 defective and 4 non-defective is just the following. It's going to be the product of our 2 combinations. So we're choosing 1 of the 4 defective, and then times us choosing 4 out of the 116 non-defective. So we work out using our formulas what that will be for combination for a result of 28,640,980. So the number of ways of selecting 5 fasteners is from the 120 is 120, choose 5. And so the ways of selecting these 5 is 190,578,024. So we have to put these two together. So the probability of selecting exactly one defective fastener is the following. So we had our totals from before that we already figured out, but here's our formulas. So we're choosing the one defective and then the 4 non-defective. That's our numerator, and we're choosing that out of all of the choices where we select 5, the different ways of selecting 5 out of the 120. So we already got those numbers earlier. So our probability is about 15%. So the probability of randomly selecting exactly one defective fastener is 15.03%. So if we selected 5 fasteners 100 different times, we would expect about 15 of the samples to have exactly one defective fastener in it. That's just a translation for what we got with our number here. Okay, that's it for this one. Thanks for watching.